In section 6.2, we discussed transforming combining random variables. And instead of finding the entire distribution for these combinations and transformations, you're allowed to take shortcuts with the means and standard deviations of the total or difference or the transformation of the random variable. We're going to talk about those shortcuts today in this video and other videos to follow on 6.2. We're going to revisit a situation from 6.1 with the roulette table. We had a certain bet, $10 bet we found the expected value and standard deviation of. A question posed would be, would it be better for a person to make two $10 bets on a roulette or a one $20 bet on roulette? You know, which one would be better for the actual person playing the game? So the question is, are you going to make more money if you bet $20 once or $10 twice? So you maybe think to yourself, well, it's the same amount of money, so that might not matter. But you are spreading out over two different plays of the game, so that may matter. So what math's going to help you answer this question? Well, I would find the expected value for each. An expected value is also called the mean, Greek letter mu, for each. And the bet with the higher expected value should yield you more money in the long run. Okay? Now, we already know what the expected value is for a single bet in roulette for $10. It's about negative $0.53. But making two consecutive bets, we have not done that yet, and hence why we're doing combining random variables as part of this set of notes, which is why this question's actually included here. We're actually going to figure out how to combine two random variables into one big variable and find that new mean as part of these notes. So finding the new mean for the new type of bet, the two $10 bets, the $20 bet we already know how to find, compare those two later to see which one is higher, okay? Now, the majority of the information on linear transformations is old. So for example, adding or subtracting a constant a. If you add or subtract a constant a from every data value in your distribution, you should have some things that are affected and some things that are not affected. So for example, if you add or subtract a constant, what's affected? The center and location measurement. So mean, median, quartiles, and percentiles. If you were to add 10 to every data value in your data set, mean, median, quartiles, percentiles would all increase by 10. Same thing goes with subtraction as well. So the center will change. What doesn't change when you add or subtract is your shape or the measures of spread, so range, standard deviation, and IQR. Those will not change when you add or subtract. Now, if you were to multiply or divide by a number b, mean, median, quartiles, percentiles still change. So the center will change if you multiply or divide. However, what's different about multiplying or dividing is that the measures of spread actually change too. Range, IQR, and standard deviation. So everything gets changed when you multiply or divide except for the shape. When you multiply or divide or when you add or subtract, the shape does not change. So if you have a normal distribution to start off with and you multiply or add or both, the shape doesn't actually change. It's still a normal distribution. And if you'd like to look at a web diagram of what that actually looks like, here it is. We have linear transformations, the two types, add, subtract, multiply, divide. This changes measures of center and location. It does not change measures of spread or shape. Multiplication division changes both the measures of center and location and the measure of spread. It does not change the shape though. Okay. So this is in the copy of the notes on the website, so you can copy those down if you need to or take a picture of them. So we're going to start off with an example from the book called Pete's Jeep Tours example. We're going to use this throughout the notes video to help us display what happens when you add, subtract, multiply, or divide by a constant to each variable. So in the book, we have Pete's Jeep Tours example. This is the probability distribution. The number of passengers X is 2, 3, 4, 5, 6. Nothing less than 2, no more than 6. The probability for each from the book, 0.15, 0.25, 0.35, 0.20, 0.05. We always double check to make sure those add up to 1. They do. So this is a legitimate probability distribution. To find the mean and standard deviation, you can use your TI-84. The top X values go into L1. Your probabilities go into L2. And you get the mean of X is equal to 3.75 passengers. And you also get the standard deviation, 1.09. So, randomly selected day, this is your average passengers. On randomly selected day, the the values differ from the mean by 1.09. The two main things you get from TI-84, very simple to plug in and calculate as well. Let's try and do a transformation now. So we know that Pete charges $150 per person for his Jeep rides. We're going to change or make a new variable C equals the total amount of money that Pete collects on a randomly selected trip. They ask you to write an equation representing the relationship between X and C. This is a skill you need to have for an assessment. Be able to take this information and disseminate it into an equation with an equal sign with the variables C and X. So C is going to be equal to 150 times X. This is the amount of money per passenger. This is the number of the passengers. Simple multiplication will give you the average the average money taken in. So our variables on top, C, are going to change. You're going to take the previous X row and multiply each number by 150. And those numbers are 300, that's 150 times 2, 450, 150 times 3, 600, 150 times 4, 750, 150 times 5, and 900, 150 times 6. Notice the probabilities do not change. They will remain the same. Only the variable changes along with the values for the variable. So we're going to refine the mean and standard deviation with this table, compare it to the previous mean and standard deviation, compare the respective histograms as well. So we're going to find mean and standard deviation of this using our graphing calculators. So this is L1, this is L2. Redo the calculations, and here's what you get. 562.5 for the mean and 163.46. So you might be thinking to yourself, well, typing that in wasn't a big deal. There was only 5 in each list, so I don't mind doing that. But what if the list was 20 items long? What if it was 50 items long? Nobody's going to want to retype those into the calculator. So let's try and figure out if we have any shortcuts. Okay. Well, this number here is the mean of the new variable C. And the rules state that the mean should change by the same factor as each value did. So the mean of the new variable should be the mean of the old variable times 150 from the previous information given about the problem. So the old mean was 3.75. If you multiply that by 150, you get 562.5, which is the new mean. So instead of retyping this into the calculator, you can simply use this equation to help you find the new mean. Let's see if it works with the standard deviation as well. Because when you multiply it by a number, remember both the mean and standard deviation change. So the new standard deviation should be the old standard deviation times 150. Well, that was 1.09 times 150. And when you do that math, you get approximately 163.5. And with some rounding, you'll notice they're pretty much the exact same number. We just didn't round here, but here it did get rounded. So 163.5, 163.46, essentially the same thing. So this here is your shortcut for finding the mean, and this is your shortcut for finding the standard deviation. All you have to do is multiply your mean and standard deviation by the factor you multiply every single data value by. So instead of retyping this into the calculator, use these two shortcuts to find the new mean and new standard deviation. It's just a factor 150 difference. Now, the histograms. Let's compare those last. Look at the shape here. Look at the shape here. You'll notice the shapes are identical. Okay? The heights are a little bit off because of the scaling is different for this graph and this graph. The x-axis changed based on multiplying by 150, so those numbers are different from these numbers on the x-axis. But the basic shape itself is exactly the same, and that's what we illustrated this is an illustration of what we talked about on the front page, where when you multiply by a number, the center, the spread, change, but the shape does not. All right, let's write an even newer equation, and we're going to talk about actually paying for stuff. Pete's got to pay for gas, permits, ferry, pass for each half-day trip. The amount of profit V that Pete makes from his trip is the total amount of money C that he collects from his passengers minus 100. So minus 100 essentially tells you exactly what operation we're talking about. So V is going to be equal to C, the money he collects, subtracting 100. Now, think about what happens when you subtract a number from each data value. The mean will change, but the standard deviation should not change. Okay, so let's actually write these out. So the previous table, those numbers, minus 100. So this was 300, now it is 200. This was 450, now it is 350. This was 600, it is now 500, 650, 800, and so on. Notice the probabilities did not change. They are still the same, but the variable values do change. Okay, we're going to find the mean standard deviation again using the TI-84. And when you do that and type it in, you get 462.5 for the mean of V. Sigma V, standard deviation, is 163.46. We're going to compare those to the previous numbers. So mean of C from the previous page was 562.5, and the standard deviation was 163.46. Now, you'll notice this and this are not the same. They're actually 100 apart. If you take this number, subtract 100, you get this number. Where does 100 come from? This basic equation, the fact that you subtract 100 from every value of C to get the new variable V. So a shortcut to find the new mean of V would be the old mean minus 100. Okay, this is your shortcut. So if I were to continue to work here, 562.5 minus 100 would be equal to 462.5, which is my actual new mean. Okay, so in this information here, this right here is your shortcut. So no need to retype this into the calculator and recalculate it. You can just do this shortcut right here. You also could just do it without the distribution. I could give you a mean standard deviation, and you would be able, without the calculator, using the L1, L2, find the new mean standard deviation because you understand linear transformations of distributions. Now, standard deviation, new of V and the old one of C. You'll notice they're exactly the same. We kind of talked about this before when we started the problem. When you add or subtract a number, it does not change the measure of spread, so therefore we expected this not to change. So the old standard deviation will be equal to the new standard deviation here because we subtracted 100. If this number, if this were multiplication or division, this would change by the same factor. But because it's addition or subtraction, in this case subtraction, this does not change. This does, the measure of center, mean, but standard deviation does not. Okay. This table below, these two boxes, top two are old information. It's the same exact information from the front page. This down here is the new stuff. General effect for random variable with linear transformation y equals a plus b times x. A and b are your numbers that you add or subtract, and b is your multiplication or division. So what actually happens here? See if we can read this one at a time here. So first, the probability distribution for y is the same as x's if the probability distribution, if the b value is greater than 0. So if it's a positive b value, your probabilities will remain the same. 2, your mean. You will add a and then multiply by b. Multiply by b and then add a, if that's the order of your equation. If you're talking about means, a and b both affect mu. Okay, they both affect the mean. If you're talking about standard deviation, only b does. Even if you were to add a, this will not change. You'll notice that the relationship here, there's no a mentioned in this equation because a, when you add or subtract a, has nothing to do with the new standard deviation. Now, the absolute value is something we have not talked about yet. In case b is negative, we use absolute value because standard deviation is a measure of spread and it cannot be negative. So even though if we have a negative 100 or negative 150 instead of positive 150, we still multiply the standard deviation by 150. We use the absolute value here. Okay? So just to recap, the rules for linear transformations. If you add or subtract a value, A, to every value or every data value, random variable value, only the mean changes, not the standard deviation. If you multiply or divide every value by some number B, the mean and standard deviation change. Okay? In both of those instances, though, if you add or subtract or multiply or divide or both, the shape does not change. And that was illustrated by the first example with the Jeep and comparing the cost histogram with the old histogram of number of people. So this right here, that's the old histogram, new histogram with the cost. They're exactly the same shape. Okay?